Thank you very much, and apologies on the time zone mix up there. But very happy to be here and excited to talk about some work. This is from the Balanced Networks track, and I want to talk about balanced networks for working memory and neural integration. Just to introduce things. In many memory and decision-making circuits of the brain, we see an accumulation that is a mathematical integration in the sense of calculus and maintenance of signals for on the time scale of 1 to 10s of seconds. So here's a cartoon version of that. Stimulus is shown in yellow. While the stimulus is present, neuronal activity is accumulating, mathematically integrating that input. And then in the offset of the stimulus, the value of that accumulation or the value of the stimulus is stored in working memory. And I want to note that this can be an analog storage corresponding to the accumulation value during the accumulation period. Now, this has been a long-standing puzzle in the theoretical neuroscience and community, and for a very simple reason, that most neurons intrinsically have very brief memories. That is, if you present an input stimulus and turn it off, typically the neuronal or synaptic time constants are in the orders of tens to hundreds of milliseconds, not the 1 to 10 seconds of working memory. So the big question for today is, can cortical-like balanced networks generate persistent neural activity and perform neural integration? I just want to sort of set us back to the beginning in looking at classic balanced networks. So this is from the original groundbreaking paper of Carl von Vrieswijk and Chaim Sampolinski. And it had the following sort of classic excitatory, inhibitory, recurrent cortical architecture. And when you looked at an individual neuron in those networks, well, there was a certain amount of excitation which fluctuated over time, and a certain amount of inhibition shown here in the bottom fluctuating over time. But the net input to any current was close to zero. And in particular, it was fluctuations of that near zero net current that caused spiking, and that led to the classic irregular firing that's a hallmark of cortical neural activity. But from the point of view of talking about slow timescale persistent activity, these networks, they went on to show, have a very fast response. They said an advantage of them is that they could very quickly and closely follow external inputs. But this means if an external input turns off, these networks would quickly turn off. That is to say, they're not good for memory storage. So instead, going to other classic work, memory models haven't been based on balanced networks. They've been based on positive feedback. And this is overwhelming across many, many different models. When you distill them down to their essence, they come down to something like I'll show on this slide. So the idea here is that an input coming into a neuron, if it comes in, a typical isolated neuron, its firing rate will go up and then come down, quickly decaying on some neuronal or synaptic timescale. But of course, neurons aren't in isolation. And the point is that when they're not in isolation, they're connected in a network, they can now have persistent activity and respond to a command input. And if there's a second input, they can furthermore increase their level of persistent activity, that is, temporally integrate the input. How does this occur mechanistically? Well, the story is this command input, comes in. If the neuron were in isolation, the activity would decay away, but there's positive feedback. So there's positive feedback through recurrent excitation that can sustain the activity. And there's also another form of positive feedback through a double negative form of positive feedback or recurrent disinhibition. And when this is tuned properly, this feedback can exactly offset the natural leak in the neurons so that basically activity can be maintained as the feedback is canceling the leak. And if a new input comes in, the input can again drive the neuron to increase its firing rate and hold that increased firing rate. So this is an analog form of persistent activity in the absence of input. Okay, but what's the problem with these networks? Well, now let's look at the two different neurons. We see neuron 1 here stepping up its activity. Of course, the recurrently the recurrent inhibition means that the other neuronal population, population 2, decreases its activity when these commands come in. And what this means is it has strong implications for thinking about the balance or lack of balance of synaptic currents coming into any given neuron. So now let's look at, up here, these inputs coming into neuron 1. So we have excitatory inputs highlighted in green, inhibitory inputs highlighted in red. And now let's think about what happens as neuron 1 increases its activity. So we're plotting here on the y-axis, the inhibitory input to neuron 1, on the x-axis, the excitatory input to neuron 1. And now here's neuron 1's firing rate. As neuron 1's firing rate increases, shown in a diagonal, each of the points here indicates the amount of excitatory and inhibitory input. And you can see that these are imbalanced. At 30 hertz, there is one value at which there can be a balance, then inhibition and excitation is exactly balanced. But as the neuron increases its firing rate, it gets more excitation and less inhibition, and vice versa. If its firing rate decreases, it has reduced excitation and more inhibition. So this shows that the classic positive feedback models are not balanced in general, or they are balanced at only a single firing rate. So just to make really clear, this does not look like cortical networks. And this is some work from originally David McCormick's lab showing during persistent activity, the inhibitory conductance and excitatory conductance coming into various neurons. And what you see is this classic positive correlation of the inhibitory and excitatory conductances. In other words, they're moving around something similar to a 45-degree line, with some fluctuations. But the point is, when inhibition goes up, excitation goes up. And that is exactly opposite what the positive feedback models look like. Okay, so what this suggests is maybe we need a different principle. And in work a number of years ago with Sukbin Lim, we actually looked at a different framework for thinking about how persistent activity could be maintained. And it came from control theory. And it came from a sort of basic result in control theory that strong negative feedback of a signal produces an output equal to the inverse of the negative feedback signal. That is to say, if there's an input X, which goes through some transformation, can be linear or nonlinear, to produce an output Y, and then the output Y is fed back very strongly through some transformation, in this case a derivative, then the output Y will be proportional to the inverse of that transformation, and the inverse of a derivative, of course, is an integral, so that you'll get that Y is proportional to the integral of X. Let's translate that to a memory circuit and get what the essence is. So here is the basic cartoon. We have a memory cell, and it's going to receive negative derivative feedback. Well, what does negative derivative mean? It's really a slip detector. Every time the memory starts to decay or grow, it's being opposed by this slip detector, and that's being fed back with some strength W derivative. So now if we take our garden variety simple model of a neuron, linear model, tau drdt equals minus R plus its inputs, now we have a negative derivative feedback input. And you can very quickly see that a negative derivative feedback on the right is the same as mathematically equivalent to just increasing the time constant of the neuron. So this is how we can get very slow persistent activity, is basically the strength of the derivative feedback corresponds to the time constant of the neuronal decay. A more physical picture is that having a term which is proportional and opposite to the derivative is like viscous drag. So it's like having it in terms of the attractor formalism for memory, it's like putting molasses or a very viscous substance so that the state of the system decays very, very slowly. It does still decay, but very, very slowly in a way that allows for long time scale persistent activity. And that means basically, again, if the activity were going to decay, there's a positive corrective signal opposing that decay, or if it were going to grow, there's a negative corrective signal opposing that growth. Okay, so now the question is, how can this play out in neural circuitry? How can we build a derivative in the neural circuitry? And a very, very simple architecture does this, and that's shown right here. So here we see a neuron with just a firing rate neuron characterized by its rate, R of t. And imagine that we have a slow positive feedback pathway shown here and a fast negative feedback pathway shown here. And just to remind you, just very trivially, that negative of a derivative goes as R of t minus dt minus R of t. That is, putting it into the context of firing rates, we need to have feedback that has equal amplitude, coefficients 1, but offset in time to perform the derivative operation. So negative derivative feedback naturally arises when positive feedback is slower than negative feedback, and when the amplitudes of these are equal, so excitation and inhibition are balanced. And one can just carry through the math, and it's in this paper. But if you label the strengths of these connections as J and refer to the positive feedback pathway as having a time constant tau plus and the negative feedback pathway as having a time constant tau minus, then one gets that the time constant for the network goes as W derivative, and that goes as J, the strength of the input, times the difference between these time constants. And this immediately shows why the classic work did not produce this slow, persistent activity. The classic von Vrieswijk and Sampolinsky work had the same time constant on each of their pathways. So we didn't have this derivative feedback effect. Okay, well, this is a very toy model violating Dale's principle. So how do we flesh this out into a more cortical-like network? Well, we have one which again looks like the classic von Vrieswijk Sampolinsky one, except for the time constants. We have an excitatory pool, an inhibitory pool, and here we have the slow positive feedback pathway. And if this inhibitory loop is fast, then we have a fast inhibitory feedback pathway. And again, if those pathways are balanced in strength, but with these appropriate time constants, we get derivative feedback. Okay, so let's check that this actually works and maintains persistent activity and performs neural integration. And that's shown here. Indeed, it does. So this is showing response to two different types of inputs. On the left, you see the response to pulse inputs of 3 different amplitudes. And you can see that the firing rate, again, maintains persistent activity as very slow decay. And that's due to the slip correction of the derivative feedback. In response to steps, this shows that it really is a mathematical integrator. In response to 3 different levels of step inputs, you can see 3 different slopes of accumulation, of ramping activity. So it really is an analog memory network which can temporally integrate its inputs. So are there interesting properties about this from this network that you don't get in the positive feedback networks? And that's shown, and indeed there are, and that's shown here. So what I'm going to show you here is the effect of perturbations on the network. And one of the things that's well known is that these networks, which are mathematically line attractors, are very not robust. And typically for the positive feedback networks, they're not robust to almost any perturbation one can imagine. So here's just the cartoon of a simple excitatory positive feedback network. One could also do the double inhibitory one. But if one kills some fraction of the excitatory cells, or in the double inhibitory one, kills some of the inhibitory cells, or changes gains, or scales excitatory inhibitory synapses, or puts any nonlinearities in, the network detunes. And that's because basically any of these manipulations will remove or disrupt the positive feedback. So this is showing in green either +2 or -2% changes in the feedback level or in the number of cells. And you see already dramatic loss of the persistent activity. Now in the middle row, look at the derivative feedback network. Now imagine killing some fraction of these excitatory cells. Well, killing those cells doesn't disrupt the time constants in the network, so it doesn't disrupt that positive feedback is slower than negative feedback. And likewise, in terms of the strengths of the inputs, killing some of the excitatory cells, well, it reduces the excitatory feedback pathway, the positive feedback pathway, but it also equally diminishes the negative feedback pathway, so things still stay in balance. And therefore here showing 10% increases or decreases in whatever of these perturbations, killing cells, increasing gains, etc., hardly changes the activity at all. And can one have a combination, kind of have one's cake and eat it too? Yes, one can. So by adding a little bit more excitatory feedback, one can have a net overall positive feedback, and then one can have perfect persistent activity and also this robustness to perturbations. Okay. So another property I said of balanced networks is that they have irregular spiking. So we also built a spiking model with populations of excitatory inhibitory neurons. And this is showing just one of the many levels of persistent activity it can maintain. And you can see the very irregular spiking. And if you actually calculate the CVs of these the spike trains of different neurons, you get a distribution across neurons. This was actually like really a mean field type model where everything was just randomly connected. So it was balanced, it was loosely balanced, it was balanced on average in a mean field sense. But you see this distribution of coefficients of variation in the interspike intervals looks very much like what people see in working memory experiments. Again, high, CVs of 1 or between 1 and 2. All right, so to compare this to the positive feedback network that I showed you, well, that one was one where there was competition between two populations. And here we set up a competing EI networks, if you wish. So here's this, again, this motif of the E and the I, and again, it's going to have slow positive feedback and fast negative feedback, but now they compete because the excitatory neurons from one pool excite the inhibitory neurons of the other pool, and any mutual excitation, it can be removed entirely, but it was weak. One gets out of this persistent activity. Again, here's population E1 and population E2, where one population goes up when the other population goes down in response to an external input. Again, it's robust against changes in synaptic weights. But importantly, what I want to show you is, unlike the positive feedback motif, now if we look at the inputs, let's say onto neuron 1, the excitatory inputs and the inhibitory inputs, that's what we're plotting here, the inhibitory inputs to E1 on the y-axis, the excitatory inputs to E1 on the x-axis. Now you can see that as E1 moves through different firing rates, these inputs remain balanced. So we have a balance of excitatory input throughout the firing range, which looks more like what we think of as the experimental motif of increased balanced excitation and increasing excitation and inhibition together in cortical networks. Okay, so from the last little bit of this talk, I'd like to actually switch to not just talking about just balanced networks for storing one memory, but talking about spatial patterns of input. So this is a classic experiment from Funahashi and Goldman. A monkey was asked to fixate, and then a light came on at one of 8 locations in a circle. When the light went off, the monkey had to make a saccade, and different neurons were tuned to different locations. So this is showing the activity during the D is the delay period for different neurons. And this neuron shown here was tuned to angles between 90 and 180 degrees, Q locations between those, and didn't respond to other Q locations. And the question is, how can patterns of neural activity corresponding to this type of behavior be carried out? And there's a very classic architecture for these spatial working memory tasks. It's known as the ring model. There's a ring of neurons. They're connected locally by excitation and more distally by inhibition. And these do a great job of by symmetry. They can encode any location of a spatial input, but they don't encode amplitudes of the inputs. So this is shown on the right. So if the input is small, there's no activation in the network. If the input is 0.1 or even 5 times that, 0.5, you get exactly the same activity during the memory period. It's an all or none response, and there's no encoding of input amplitude. And the question I'm going to ask and what I'm going to show is, can a balanced ring model encode amplitude information? So the architecture now is going to be similar to what I've shown you before. There's going to be this core of this EI motif with slow positive feedback and faster negative feedback. And then I've unrolled the periodic connectivity. But what you can see is, again, there's going to be lateral inhibition and lateral excitation defined by weight matrices of the populations JEE, JII, JEI, JIE with appropriate time constants to have slow positive feedback and fast negative feedback. So what's the key principle here to make a balanced network in these spatially extended networks? Well, the key principle is to use Fourier analysis. So again, if you're going to see a firing rate pattern that's sustained like the following one, you could break it into its Fourier components. There's a DC component, there's this component, first cosine component, a second cosine component. And the idea is any component of activity that can be maintained is maintained by derivative feedback on that component. That, of course, leads to the question, how do you form this derivative feedback on the components? Well, without getting into the details, the way you realize this is you do a Fourier decomposition on the weight matrices, so that for any component of the weight matrix, you can break it into its Fourier components. And now we have the same balanced network that I showed previously, but the tuning that needs to be done is there needs to be, again, slow positive feedback, fast negative feedback with a balance of the strengths of the connectivity within any Fourier mode. When you do this, and I should make clear that even though it uses a Fourier decomposition, it still works with nonlinear neurons. So that's a nice feature of it. You can now maintain memory activity for different amplitudes of inputs. So what's being shown here was four different trials with 4 different levels of input from orange up to blue. And you can see that the amplitude of the input is now stored in the persistent activity pattern. So the bump of activity can now encode amplitude information. And what I'm not showing you for the sake of time is that the network will also temporally integrate inputs of a given spatial location. And it's also robust to either local or global perturbations of cells in a way analogous to the network I showed you earlier. So to summarize, what I've shown you is that classic balanced networks have fast dynamics, and classic working memory and neural integrator networks are based on positive feedback and are not balanced. What I've shown you instead, if one wants to make a slow dynamics network that maintains slow persistent activity and performs neural integration, that can be done through negative derivative feedback networks that are based on the principle of balance, excitation, and inhibition, but now with slower positive than negative feedback. These are robust to many common perturbations, such as death of cells, and the properties extend to nonlinear spatial memory networks by Fourier analysis. Thank you.
Thanks so much, Mark. Great to hear. Are there any questions?
Reiner?
I have a couple of questions. So with the spatial networks at the end,
Yep.
So you have, I hope you understand this, but you have spatially varying connectivity strengths.
Yes, so the connectivity strength is spatially varying. So the simplest thing you could do, which would be similar to the original ring models, would just be to tune the first cosine component of the connectivity, and then what you get is a network which always holds a bump with a cosine shape. But the key thing is, again, when you break down the spatial connectivity around the ring into its Fourier decomposition, then you're going to have the excitatory to excitatory feedback it's actually shown here. So the excitatory to excitatory feedback in that mode has to equal the negative feedback, which would be JEI, JIE, that's going around the loop, and then it's normalized by the JII term. So that's the condition right there, and equality between those maintains the balance, and you do that within the Fourier modes.
Right. How do you do that computation? Does it get very complicated, or it's just?
Computationally, you literally just say, I want this connectivity, and then you just do a Fourier analysis. You just stitch together the sines and cosines.
I see.
Yep.
Oh, very interesting.
And then you end up with the overall connectivity for the network.
I see. Yeah, very interesting. I was also wondering, so what parts of the brain exactly were you saying are these balanced networks present, like sort of all over, or any parts in particular?
Yeah, so I would love someone to do the experiment. No one's actually done the intracellular recording experiment in vivo during an analog working memory task or a neural integration task, which also requires, of course, not just doing the experiment, but first localizing where that activity is maintained, rather than possibly just looking at a readout, which wouldn't have to be balanced. I think, but one thing would think of this as something like in the frontal cortices.
Okay.
At least I think it may be the wrong layer of neurons, but there were some studies showing that, for example, the NMDA receptors in the E to E connections are slower than the NMDA receptor kinetics in the E to I connections. So that would actually be the right way to have this, the right way to have the kinetics, at least the slower positive feedback, the negative feedback connectivity. For the balance, it needs to be shown experimentally, but the idea would be, given one sees irregular firing, and at least in, I believe the McCormick work may have been either slice or anesthetized work, at least their excitation and inhibition go up and down together. This is what one would expect.
Okay, interesting. We have a question in the chat you might see from Ganendra Singh. He asks, how much is it different from the Cowan model with feedback mechanisms?
Yeah, so I mean, this is the basic Wilson-Cowan model. The real key thing in here is, this is both similar to the Wilson and Cowan. It's also similar to the, von Vrieswijk, Sampolinsky architecture. The real key thing was one simple change. And the one simple change is just to make this synapse right here slow. This JEE synapse slow. It actually also helped. The positive feedback also includes the JII if you work through the math, and you can think of inhibition is like positive feedback. So the overall positive feedback time constant is tau EE plus tau II, and that needs to be greater than the negative feedback pathway, which is going around this loop, tau EI plus tau IE. But so that's the key thing, is changing the time constants.
Okay, thanks, Mark. There's another question here from Jung Kim. Can you see it in the chat? Okay, so you're saying,
right, so
you can speak.
Scroll down, yes. Yeah, can you still have a nonlinear neuron and have it apply to the neural integration? So that, so I showed actually in, I guess, the next slide after this one, that actually this neuron is nonlinear. So you can, and the nice thing about, and the way to think about that nonlinearity is the input-output function of the neuron being nonlinear doesn't really cause a problem, because you're not disrupting that it receives that the inputs coming into the neuron are balanced, and you're not messing up the relative time constants of the excitatory and inhibitory feedback pathways. So the nonlinearity doesn't disrupt that. Now, will with this output nonlinearity, will it strictly be a mathematical integral? It does look like I think it still does linearly integrate. And again, the key thing goes back to this control theory result, that if you feed back a derivative very strongly, it overrides the intrinsic properties of the network. And then you get a very linear response. The same thing occurs, actually, Bart Ehrmantraut wrote a paper years ago talking about how you get linear firing rate versus current injection relationships in conductance-based neurons. And again, it was a very similar principle of having very strong negative feedback overriding the other intrinsic channel properties, so that those details didn't matter so much. So I think that, so the basic principle is that you're not messing up the derivative feedback, and you're not messing up the balance of inputs.
Okay, well, thanks